I'm really happy to have Matthew here, Matthew Burgess, to give us a talk. It's really cool. We haven't met before, even though our groups are quite related. He's from the Chris Costello group. That's where you did your postdoc. Yeah. And Juliano, where are you? He was there too before he came here, so he made the connection. You got him to give us a talk. So thank you for that. And please give us suggestions. We're open, first come, first serve. There is good people, interesting people to do amazing stuff. You know why I'm so happy you are here? You started your professorship at when? When did you start your position?
2 months ago.
2 months ago. So this is really good for all of you students about to finish postdocs. That's an example of where you are going to be in a few years, okay? So have your faculty position and do amazing stuff. So thank you, and he will be giving us this talk. I don't need to say much, but I'm really happy you can see that. So over to you.
I'm embarrassed that I've never been here before, because this is like the place for fisheries. But so it's really, really great to hear. Thanks, Rashid. Thanks, Juliano. Thank you all. Okay, so I want to start by reviewing the Fisheries 101 synergy story and trade-off story regarding fisheries and conservation. So here's the synergy story. It involves target stocks. If we're fishing a target stock, there's going to be this bell-shaped relationship between sustainable catch and abundance. If there's no fish, you can't catch any, so it has to go through the origin. You can't have infinite fish, so at some point there's got to be a natural limit to how many fish you can have, so there's got to be another x-intercept, and maybe it looks something like a bell in the middle. So we all know that the point at the top is the maximum sustainable yield, and we also know that if we're overfished, if the abundance of the fish stock that we're targeting is lower than the maximum sustainable yield abundance, then rebuilding it has a positive impact on both the yield and the biomass. It's a win-win, and it probably also has a positive impact on the profits. So win-win-win-win. Here's a real example of where this might have happened. This is the U.S. Atlantic sea fishery from the Middle Atlantic Bight. And in 1994, there was a management change, moratorium on new permits. I think there were some closed areas, a couple of other, and you can see that not long after the LPUE, which is an index of abundance in black, goes up, and the catch rate also go up. More fish in the water, more fish in the net, win-win. My former boss, Chris Costello, and some of his colleagues tried to quantify a couple of years ago how big this win-win might be at the global scale for a little over 3/4 of the stocks in the world. And the answer is pretty big. So if you look, for instance, at China, China can get about just under $10 billion in additional profit and something like 100 million metric tons in additional biomass and close to 1 million metric ton in additional catch. Those are 3 big wins. And again, this analysis is based on these kinds of models, species models that I was showing previously. So that's the classic synergy story. The classic trade-off story involves bycatch. So with bycatch, we're catching species at the same time with the same hooks and the same net, and so we might have some maximum sustainable yield mortality that we want for the target species, and there might be some conservation, some mortality limit we don't want to exceed for the bycatch species. And the problem when you're catching them in the same net is that you can't choose any point on that graph. You can't choose any combination of mortality you want because you're catching them in the same net. You might instead be constrained to some relationship that might look like this, where, again, you don't fish, you're not killing anybody, so it goes through the origin. And then as you increase effort, there's some relationship that's predictable, driven by the gear and the species biology, between the mortality you inflict on the bycatch species and the mortality you inflict on the target species. And in this example that I've drawn, there's a trade-off. You can have maximum sustainable yield for the target species if you want, if you're willing to exceed the conservation limit of the bycatch species. Or you can limit bycatch to be within the conservation limit for the bycatch species, but then you have to underfish your target species. And so you have a trade-off between fishery and conservation in this context. A real-world example where this might be going on is the turtles bycatch in the Hawaiian longline swordfish fishery, where we've got a stable swordfish population. We're fishing it at below the FMSY, but we closed the fishery between 2002 and 2004, and then again in part in 2006 because we caught too many turtles. This seems to be an example where, in order to protect turtles, we're underfishing this target fishery. And if you look at the IUCN red list and you count up how many populations are threatened, declining, and where bycatch is the main threat or one of the top two main threats, we counted there are about 26 marine mammal populations, 8 sea turtles, 22 seabirds, and a bunch of other kinds of species. So you might think that these populations present this kind of a trade-off. Okay, so to recap, the conventional classic synergy story is that if you rebuild overfished target stocks, you get a win for yield, profit, and biomass. And the classic trade-off story is to protect bycatch, you have to be willing to get some profit and yield from your target fisheries. So for the rest of this talk, I want to argue that there might be quite a large number of cases, not all the cases, but quite a large number of cases, maybe disproportionately concentrated in developing countries, where it's totally the reverse of what I just said, where the win-win between rebuilding overfished target stocks and protecting bycatch species at the same time by virtue of fishing less, and where the trade-off might be, because of trophic interactions, yield and that we might increase our yield by collapsing the food chains in some of these ecosystems. Let's start with the bycatch story. We often assume that we have this trade-off, but often what we measure is just how much bycatch there is. And if we measure that current bycatch is unsustainable, that it's higher than its conservation limit on the y-axis, does that tell us that we're in this trade-off world? That this is the relationship between target species mortality and bycatch species mortality? And therefore, in order to sustainably manage our bycatch species, we have to underfish? Or might we be in this world? Same bycatch mortality, but here, the story is not that you can't have both sustainable yield, bycatch fishing and maximum sustainable yield. Here the story is you're overexploiting your bycatch species because you're overexploiting your target species. And so if you scaled back mortality a little bit, you could solve both problems at the same time. Then your conservation limit, and you can get maximum sustainable yield. And so for the list of IUCN threatened species that I mentioned earlier, my colleagues and I tried to figure out, for as many of them where we could find enough data, which of those two worlds are they living in? Are they living in the trade-off world, where we really have to constrain in order to protect them? Or are they living in this win-win world, where the fact that they're endangered might almost be a symptom of the fact that we're overfishing the target species? And basically our strategy was to look at data on these populations and compare it to data and models from this Costello et al. Paper on most of the world's target stocks. And the basic idea is, if we're going to try to do this analysis by looking at all the fisheries in the world and seeing, how many turtles are they catching per hook, we're done. We're never going to be able to get enough data to do that. Instead, what we wanted to do was figure out proportion. By how much do you have to reduce mortality on each bycatch population to halt or reverse its decline, its population decline? And by how much do you have to decrease mortality on the target species to get maximum economic yield, maximum profit? And we did a similar analysis for maximum sustainable yield with slightly less optimistic, qualitatively similar results. So I'm just going to show the profit version. So here's the macro scale picture. On the left, we're looking at the bycatch populations. And we have, for each one, we have two of a measure of their current rate of population change, a measure of their bycatch mortality rate, or a measure of what their rate of population change would be without bycatch. All we need is two of those things, and we can calculate the other one by an equation that I think is on my next slide. Maybe not. And the color tells you the fraction, the proportional reduction in mortality you need to stop each population's decline. Now, one thing you'll notice is there are a couple of populations that, according to best available data, bycatch, you can completely catch, and some others are going to get them anyway. Those are the ones that are below the diagonal. For others, the Kita up there in the top left, you need to almost entirely catch, and we don't have a Lee effects in our model, so even that is probably optimistic. But you can see that there are some here where you're not talking about that big of a reduction in mortality proportionally, and if you compare that to the estimates from Costello et al. Of how much reduction in fishing pressure you'd have sort of as a weighted average across the target stocks in each region, you can see just by visual comparison that it's probably not the case that every species is in the trade-off category. There are probably some that are in the win-win category. It's also probably not the case that every species is in the win-win category, right? It's very unlikely that you could have a vibrant Totoaba fishery and still save the vaquita. The other key piece of our analysis is dealing with uncertainty in these parameters, because there's a ton of it. A lot of these bycatch species are extremely data poor. And so rather than here's our best point estimate of mortality and population change, and is it bigger or smaller than the average of the target species, if we even know which of the relevant target species are for each bycatch species. Instead, our approach was, let's do a big Monte Carlo over basically all of the possibilities in terms of what the amount of mortality reduction might be that each population needs, and the amount of mortality reduction it might get if we maximize economic yield for all targets. And so on the what the population needs side, we're getting the best available uncertainty bounds from published literature on the two of those three rates I mentioned. So population decline, mortality rate, or what the growth rate would be without fishing. In cases where we don't have it, we have, you can read our 50-page supplement if you want. We have some ways where we borrow information from other species, sensitivity analysis where we doubled all our uncertainty bounds. And the point is we get a probabilistic estimate of what it might need. That's quite big. And you'll notice that in some cases, there's a chance that it's not actually declining, right? So in this case, this is the probability we assign that that it's not actually declining. And from a perspective of win-win, we still care about that because there's some fisheries that aren't being overfished. And so in some cases, maximum economic yield means fishing harder. So the uncertainty in what the population, what reduction in mortality the population gets when you maximize profit, our key assumption is that if the target species has, say, a 50% reduction in mortality under maximum economic yield, so does the fraction of bycatch for any bycatch species from that fishery. So if a third of the bycatch of a certain turtle is from a certain target fishery, we reduce the fishing pressure on that target species by half, we assume that that third of the turtle mortality also goes down by half. But we don't know what all the target species are. And of course, we're looking at single species models. In reality, you'll have fisheries with multiple target species. But we do know some things, right? We know that a turtle in the Atlantic doesn't live in the Pacific, so we can rule out all those stocks, right? We know what kinds of habitats they live in. We know what their ranges are from the IUCN. We know what kinds of gears they're caught in. And so what we do for each bycatch is we come up with a set of target species that might be contributing to the bycatch mortality, and we do a Monte Carlo where we simulate basically all possible combinations of bycatch, all possible allocations of bycatch among those target fisheries, and then apply our assumption of proportional reduction or increase depending on what's needed for economic yield in each of these target fisheries. And so in our Monte Carlo, essentially what we're doing is we have these two distributions, and each time we're drawing one point from each and saying, okay, if we rebuild to maximum economic yield, have we gotten all of the bycatch reduction that we need? In which case, great, we have a win-win. If not, then we calculate if you change the gear, how much profit or yield would you have to be willing to give up to get the additional bycatch reduction that you would need to stop the population decline? Or we did a parallel analysis where we looked at by how much would you have to make the gear more selective. Now, what's interesting about that is most of the cases we have big uncertainty on what the population needs and what the population gets in terms of bycatch mortality reduction and maximum profit. But there are some cases where the answer in terms of how big the trade-off is pretty clear, right? So in this case, almost all of our runs, there's a negligible cost. Now, one additional assumption that we look at in our analysis is that when we're calculating how much you have to give up, we assume that you can allocate reductions beyond maximum economic yield in target mortality according to principles of economic efficiency. So if this fishery is making a lot of money, then we'll close this fishery down first before we touch the fishery that's making a lot of money. And so that's partly the concavity in the profit function makes the cost lower than proportional. So there's some bycatch populations we get a very clear answer, others we don't. So this is the Maui dolphin, just caught off of New Zealand, and you can see we've got a substantial fraction of our runs where you'd have to be willing to give up more than half of the target species profits to save it, and a substantial fraction of our runs where it's basically a win-win. So the answer in this case is we basically don't know. In other cases, the answer is clear the other way, that there's definitely a big trade-off. With each of these individual populations, there are a lot of assumptions, there's a lot of uncertainty that goes in. I don't necessarily know that we've pinned down, or I don't think that we've pinned down the answer really finally for any one of these populations. But if you put it all together and ask on the aggregate, what fraction of the cases are the win-win case and what fraction of the cases are the trade-off case, I think we do get a fairly clear answer from our analysis. So the way to read this is, if you're willing to give up whatever the X value is in terms of profit, as a percentage of profit, for all your target species, what fraction of the bycatch populations could you save from decline? where the shaded green area is 95% of the runs. And you can see pretty clearly that if you're willing to give up 5% or less, you can save about half. The other thing you can see pretty clearly is that save them all, there's some that have a really big trade-off. And you can see that by how close this green area gets to 100% as this gets to 100%. If we thought there was a chance that you could save all of them for free, you'd expect to see the green shaded area hit the top of the graph before the right edge. The other thing is, it's not which species are in the trade-off case versus the win-win case is not even across the taxonomic groups. So we found most of the turtles for free. Most of the turtles seem to be this win-win case. And also regionally, places with more overfishing are going to more likely to have a win-win case than places where target species are well managed and there's still some bycatch populations that are unsustainably exploited. So to summarize, threats to many bycatch species, many bycatch populations, might just be symptoms of overfishing. But not all. There are definitely some bycatch populations where that's not the case. Now, one interesting implication of this is that if you reform fisheries to stop overfishing, you might save some bycatch species collaterally. The other thing I think is really interesting is the reverse of that might be true. So the US just passed a new import rule saying that any country within 5 years, or less than 5 years now, 5 years at the time that they passed it, that wants to continue to sell their seafood in the US has to demonstrate that their exporting fisheries comply with the US Marine Mammal Protection Act at a standard comparable in effectiveness to the US standard for US fisheries. So some of my colleagues and I wrote a policy forum on this. We try to figure out which are countries and fisheries that are going to get hammered by this rule potentially, that might have a big incentive to reform their marine mammal conservation. And so here are some of the regions, some small Latin American countries, some Pacific Island countries, some parts of Southeast Asia. Now, what I think is really interesting is, just like it's probably the case that if we fix some of these overfishing problems, we'll save some turtles and mammals collaterally, if we fix some marine mammal problems to comply with this rule, we might fix some fisheries collaterally, so long as the institutions double up. But that's not going to work in every case. The clear result from our analysis was that some of these cases are trade-offs. Okay. Now let's revisit the classic synergy story. You rebuild the target stock, more fish in the water, more fish in the net, more money in your pocket. Fantastic. The problem with that is that a lot of places that are in heavy fishing, the fish are smaller. This is a great figure from McClenachan's 2009 paper, looking at trophy fish in Florida, I believe. Here's a figure from a paper by Daniel Pauly et al. In 2005, looking at changes in the max length in different parts of the world, where the red areas are where the fish catch is getting smaller. And the thing is about that is that you have feeding relationships in fish that are size-based, and so smaller fish might effectively mean a shorter food chain. And if you have a shorter food chain as you overfish, then you might be making that food chain more productive on average, because food chains tend to be very inefficient. So harvesting lower down, you're going to get more yield. It's just like we farm corn and not deer. If we wanted to farm the same mass of deer, we need a way bigger field than we would for corn of the same mass because of trophic inefficiency. So using ecosystem models, this is a paper led by Nis Jakobsen. We looked at, using ecosystem models, where is the efficiency frontier? So if you simulate different fishing strategies to equilibrium, what's the best you can do in terms of yield for a certain amount of ecosystem health? This is an ecological indicator that basically looks at cumulative depletion across species, but adds an additional penalty for depleting a species beyond a certain level. So you sort of how much are we depleting the ecosystem, but with extra penalty for really hammering one species. And same thing for any given amount of yield, how well can you do on the ecosystem indicator? And efficient in an economic Pareto sense is anywhere on this red line. Anything outside the red line, you can't have at equilibrium. You can have it transiently, as they did apparently in the Barents Sea, but you can't have it at equilibrium. So the question was, at the beginning and the end of the time series in these ecosystems, where were we relative to the efficiency frontier, and where would single species MSY be relative to the efficiency frontier? So single species MSY is dot, the gray dot. The equilibrium you would get from the fishing pattern at the beginning of the time series is the tail of the arrow. The tip of the arrow is the same thing, but for the end of the time series. And what you can see is, in a lot of the cases, it's less that fisheries are moving towards or away from the efficiency frontier. They're just kind of moving along the efficiency frontier. Especially in these two cases, which are European waters, we're doing better on the ecosystem, but at the cost of yield. We're catching less. And so it seems to be there's more of a trade-off. An even starker example is this paper led by Cody Zawalski, where it was a similar model applied to the East China Sea. And there we found that if you did single species MSY, you'd get half the yield you have today, about. You can get a little bit more yield, but not much. Again, one of the interesting and provocative hypotheses in this paper was maybe China is not over-reporting their fish statistics. Maybe they've just collapsed their food chain by fishing so hard for so long, and thereby made their fisheries more productive than the oceanographic conditions would suggest they should be. So these analyses suggest that maybe when you're talking about yield and conservation of target species, there's this trophic median trade-off that is harder to see with single species models. Now, interestingly, with profit, you don't quite see it as much. So for instance, if you look at the Zawalski et al. Results, we're finding the value is about the same. This is MSY versus the status quo. Yep. The economist, yeah, ask questions during the talk. The revenue, yeah, we don't have cost data. Profits are higher, yep, because costs are lower. Yeah, no, that's right. So, but and that supports the idea that it's not as much of a trade-off. It doesn't seem like it's as much of a trade-off with profit. And in the paper that NIST led, it's the same thing. So if you look at we only had enough economic data to look at it for these two ecosystems, but here you sort of see what you'd expect to see with management changes over time, that you're moving in an efficient direction. The arrow going up and to the right, that suggests we're making more money and we have more fish in water. More classic win-win story that you'd expect. Okay, so food chains are inefficient, and that energetically, and that is what creates this trade-off with yield and conservation. The reason why I think it's different with profit and conservation is that food chains are not as inefficient economically, because bigger fish have higher prices. And so that price gain, as you get bigger, offsets some of the energy that you lose, the energy efficiency that you lose. The other thing is, supply. So that's sort of what this study is showing on the right here. That if you model prices, all else equal, you get a positive effect of body size. The other thing that's sort of more obvious, Econ 101, is supply and demand. If we collapse the food chain, have a bonanza of small fish, we've got a big supply, our price is going to go down. And so again, that lessens the effect of trophic inefficiency on a trade-off between profit and conservation. So, conclusion, the conventional wisdom is yield profit and target stock health go hand in hand when you rebuild overfished stocks. And the trade-off is profit and yield versus protecting bycatch species. What we found is that there seems to be a synergy between profit and target stock health in a lot of cases, and sometimes also with protecting bycatch species. It seems to be more of a trade-off than we realize with single species models between yield and conservation of large fish. And for some bycatch species, there's also a trade-off between profit and protecting them. So those are the ones we really ought to focus on for things like gear improvement. Now the beauty of science is it's never done, right? So in 20 years, some young punk is going to come in and say, Burgess said. So some important follow-up questions. Notice that I kind of implicitly contradicted myself between the first half and the second half of the talk. Where in the first half of the talk, I'm doing this analysis based on single species models about trade-offs. Then the second half of the talk, I say, well, single species models miss these big trade-offs. How do you make sense? So I think that there is a lot of work to be done to target trade-off win-win story in ecosystem context, in ecosystem models. My hypothesis the story between profit and bycatch species protection is likely to be more robust than any story regarding yield and bycatch species protection. For the same reason that the profit target stock conservation story was more robust in the ecosystem models. That profits that protect large species even at the expense of yield is good for profits. It's probably also good for endangered bycatch species. So here's the other thing that I'm writing a grant proposal on with one of my collaborators who studies turtles. Is all right. So it's great to publish a science paper saying, in macro scale terms, if you could fix overfishing everywhere, here's what you do for turtles. But that doesn't save any turtles, right? You have to go, if there really is a win-win, you have to find a way to implement it, right? And that's an inside question. It's a local question. And so I think that some follow-up analyses that need to be done, both looking at how robust is our global story when you zoom in, and what do you actually do to get these win-wins going on the ground. I think there's some interesting implications for food security of this trade-off story between catch and ecosystem health. If we fix all overfishing in China and cut their yields in half, that's going to be bad for a lot of people, probably in particular a lot of poor people. So what do we do with that? And then the question that could be on the end of basically any slide in environmental science is what happens with climate change? Climate change is going to make the trade-offs bigger? Is it going to make them smaller? I don't know. And so with that, I'll thank you. And I think I left questions and discussion.